going to start with 13.1, Permutations and Combinations. Yvette is a freshman at the University of Miami. She is planning her fall schedules for next year. She has a choice of 3 mathematics courses, 2 science courses, and 2 humanities courses. She can only select 1 course from each area. How many course schedules are possible? So one way that we can show all of the different combinations of courses is by using a tree diagram. So she's got 3 math options, so we'll call those M1, M2, and M3. She's got 2 science options and 2 humanities options. So we can make a tree diagram. So we start with her 3 math options. And for each of those math options, she can choose Science 1 or Science 2. And so that gives her 6 different possibilities. M1S1, M1S2, M2S1, M2S2, M3S1, M3S2. And then for each of those 6 options, she can choose Humanities 1 or Humanities 2. And so this tree diagram shows us all of her possible course options. And you go down each path to get the different options. And so you can list out all of them here, and you get the total is the number of options for math times the number of options for science times the number of options for humanities. So she has 12 different options. The choice of selecting a mathematics course does not affect the choice of ways to select a science or humanities course. So these 3 choices are independent events. That means that choosing one thing does not affect the probability of the second thing. Events that do affect each other are called dependent events. So try and think probabilistically of some examples of independent and dependent events. For instance, flipping a coin. Though if you flip a coin multiple times, those are independent events. Because what you get on one coin flip doesn't affect what you get on subsequent coin flips. Or rolling a die multiple times, or something like that. Dependent events mostly show up when you pick something and don't put it back. So if I pick a card from a deck and I don't put it back, and then I pick another card, that's going to be dependent, right? So if I'm talking about the probability of picking 2 aces from a deck of cards, the probability of picking 1 ace is 4 out of 52. But if I don't put that one back, the probability of picking the second ace isn't 4 out of 52 because I pulled out an ace already. So, good example of dependent events: when you pick something and don't put it back, the probability of picking the next one changes. The branch of math that studies different possibilities for the arrangement of objects is called combinatorics. The example of choosing possible course schedules illustrates the rule of combinatorics known as the basic counting principle. So one event can be chosen in P different ways, another independent event can be chosen in Q different ways, then the 2 events can be chosen successively in P times Q ways. And you can expand this for an infinite number of independent events, right? So the math, the science, and the humanities, we had 3 of them. But there's no limit to it. You just multiply the number of ways if the events are independent. If the events are not independent, things get a little bit weird. But if they're independent, you just multiply the number of ways for all of the events. Pretty easy. Vicky works at a bookstore. Her manager asked her to arrange a set of 5 bestsellers for a display. The display is to be set up as shown below. The display setup is made of 1 book from each of 5 categories. There are 4 nonfiction, 4 science fiction, 3 history, 3 romance, and 3 mystery books from which to choose. So, nonfiction, science fiction, history, romance, and mystery. So we're not deciding the order here. We're just deciding how many of each of them. So she's got 4 nonfiction books and 4 science fiction books, and 3 history, 3 romance, and 3 mystery. So choosing each of them successively using that basic counting principle, we're just going to multiply these together. 4 times 4 times 3 times 3 times 3, which is 432. Now, if these could be in a different order, that would be a more complicated problem. But for right now, since we're just picking the number, we're putting them in this order, and it's just how many nonfiction, how many sci-fi, how many history, etc., we just multiply them. So, are the choices for each book independent or dependent? They are independent events, because independent, words that I have to sound out in order to be able to spell. They're independent because picking what you put in the non-fiction spot doesn't affect what you put in the science fiction spot. So they're independent. And we said, how many ways can she choose the books for the display? 4 times 4 times 3 times 3 times 3 is, I said 432? 432. The arrangement of objects in a certain order is called a permutation. In a permutation, the order of the objects is very important. So, permutation, order matters. That's the most important thing about a permutation, is that in a permutation, the order matters. So, the number of permutations of some n objects, taken n at a time, is defined as n factorial, right? So n factorial, n times n minus 1 times n minus 2, blah, 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 all the way down to 1. So for instance, 5 factorial is 5 times 4 times 3 times 2 times 1. It's the number, and then you, all of the integers less than or equal to that number multiplied together. So 5 times 4 times 3 times 2 times 1. That's 5 factorial. You can do it with any number n. So if we have, if we're doing the number of permutations for all of the objects, it's 5 factorial, or n factorial. But what if we are not using all of them? What if we have 6 objects and we're taking 3 of them, but we want to know the number of different orders of the objects? You get this permutation formula, n factorial over n minus r factorial, where n is your total and r is your subset. It's the number that you're choosing. So, for example, during the judging of horse show at the Fairfield County Fair, there are 3 favorite horses: Ryman, Oiler, and Sea of Gus. Are the selection of first, second, and third place from the 3 horses independent or dependent events? They are dependent because once I pick first place, the probability of getting second or third place changes. So I can, once if I pick Ryman to be first place, then the probability of Oiler being second place goes from 1/3 to 1/2. Assuming there are no ties and the 3 favorites finish in the top 3 places, how many ways can the horses win first, second, and third place? So 3 horses, 3 places. That's going to be 3 factorial, which is 3 times 2 times 1, which is 6. If you struggle with the formulas, one way with permutations that you can do it is just kind of draw little spaces for the spots. So this is first place, and this is second place, and this is third place. And we say, okay, how many ways can we pick first place? There's 3 options, so we can pick 3. We have 3 options for first place. Now, once I pick first place, how many options do I have for second place? And once I pick first place, that means there are 2 left for second place. And then once I pick first and second, there's only 1 left for third. And so you multiply these together, and you would get 6. You could also do a tree diagram again, right? So my first place options are Riemann, Euler, and C of Gus. If I pick Riemann for first, then I can have Euler or C of Gus for second, and then there's only 1 option for third. If I pick Euler first, I can have Riemann or C of Gus, and again, only 1 option each for third. And if C of Gus is first, then I could have Riemann or Euler, and then only 1 option for third. So you can do a tree diagram like this. I don't know, maybe make it more tree-like. But you can do a tree diagram that shows all 6 possibilities if you want to. Or you can just do 3 factorial, or you can do a little diagram showing the spots first, second, and third, and say, okay, how many options are there for this? How many options are there for second once I've picked first? And how many options are there for third? The board of directors of BELA Technology Consultants is composed of 10 members. How many different ways can all the members sit at the conference table as shown? This is basically a line, right? So we're putting 10 people in order, which is, we're just putting all 10 of them in order, so that's the 10 factorial, right? There's 10 options of who can sit in this spot. Once we put someone here, there's 9 options for this spot, and then 8 options, and 7, and 6, and 5, and 4, and 3, and 2, and 1. So 10 factorial, which is 3,628,800. 3,628,800. That's the thing with factorials. The numbers get real big real fast. Now, in how many ways can they elect a chairperson, vice chairperson, treasurer, and secretary, assuming that one person cannot hold more than 1 office? So that's 4 positions out of 10. So this is the permutation of 10, choose 4. And so if we use the formula that we have, that would be 10 factorial over 10 minus 4 factorial, which is 10 factorial over 6 factorial, which you can put in your calculator. I'll show you how to do factorials on a calculator in class. 5,040, which is much smaller. Or what you can do is, again, give yourself 4 spaces. So chairperson, vice chairperson, treasurer, and secretary. And so there are 10 options for chairperson. Once we elect a chairperson, there's 9 options for vice chairperson, and then 8 for treasurer, and then 7 for secretary. And so if you multiply 10 times 9 times 8 times 7, you're going to get 5,040. In a combination, the order of the elements is not considered. So combination, order, doesn't matter. Very important to remember the difference between combinations and permutations. In a combination, the order doesn't matter. A combination of n objects taken r at a time is calculated this way. Very similar to the permutation formula, except you have this added r factorial. So, if you have 7 objects, so combination, say we have 7 things and we want to take 5 of them, that's going to be 7 factorial over 7 minus 5 factorial times 5 factorial. And so because of this extra term in the denominator, you end up with fewer combinations than permutations. Because, for instance, here, right, was a permutation. There's a difference between Bob being chairperson and Alice being vice chairperson, and Alice being chairperson and Bob being vice chairperson. In a combination, those two would be considered the same because they're both Alice and Bob. And so that's why you get fewer. You're eliminating the duplicates. So, yeah, the main difference between a permutation and a combination is whether order is considered, which is a permutation, or not, is a combination. So if we have objects E, F, G, and H taken 2 at a time, in the permutations, E, F, and F, E are different because the order matters. In the combinations, E, F, and F, G are the same thing. We're just taking those 2 things. So you end up with many more permutations than combinations. In 1999, the National Art Gallery in Washington, D.C. opened an exhibition of the works of John Singer Sargent. The gallery's curator wanted to select 4 paintings out of 20 on display to showcase the work of the artist. How many groups of 4 paintings can be chosen? So it doesn't tell us that order matters, right? We're not displaying them, in a line on a wall or something. It just says we're selecting 4. So if it doesn't say that the order matters, or it doesn't indicate that the order matters, we're going to assume that the order doesn't matter, and this is a combination. So combination of 20 things taken 4 at a time. And so it could be quite difficult to, list all of the possibilities of ways that we can take 4 out of 20. But that's where our handy-dandy combination formula comes in. So N is 20 and R is 4. Our combination is going to be 20 factorial over 20 minus 4 factorial times 4 factorial. And so this is 20 factorial over 16 factorial times 4 factorial. And so at this point, you could use a calculator, or we can simplify this a little bit, right? 20 factorial is 20 times 19 times 18 times 17 times 16 times 15, blah, 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 all the way down to 1. And 16 factorial is 16 times 15 times 14, all the way down to 1. And then 4 factorial is 4 times 3 times 2 times 1. So the 16, 15, 14, blah, 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 down to 1 cancels out with, you've got a 16, 15, 14, all the way down to 1 up here. So we can cancel those out because it's multiplied. And so we would get 20 times 19 times 18 times 17 over 4 times 3 times 2 times 1. So that can be a little bit simpler to put in your calculator if your calculator starts freaking out at the really, really big numbers, which does happen sometimes. And so 20 times 19 times 18 times 17 over 4 times 3 times 2 times 1 ends up being 4,848 and 45. 4,845. At Grant Senior High School, there are 15 names on the ballot for junior class officers. 5 will be selected to form a class committee. So here, there's no indication that order matters. We're just picking 5, so that's going to be a combination problem. So combination of 15, choose 5. It's going to be 15 factorial over 15 minus 5 factorial times 5 factorial, which is going to be 15 factorial over 10 factorial 5 factorial. And so because of this, we can cross out, we can cancel anything from 10 on down. So 15 times 14 times 13 times 12 times 11, and we cancel the 10, over 5 times 4 times 3 times 2 times 1. And then here is where I get a little bit fancy. I'm going to cancel the 5 and the 3 because that makes a 15. And I can cancel 4 out of the 12 to make that a 3. And cancel a 2 out of the 14 to make that a 7. And get 7 times 13 times 3 times 11, which is 7 times 13 times 3 times 11. 3003. Or, again, calculator. In how many ways can a committee of 5 be formed if each student has a different responsibility? So now the order matters. Alice being president and Bob being vice president is different from Bob being president and Alice being vice president. And so that's now a permutation of 15, choose 5, which is 15 factorial over 15 minus 5 factorial. 15 factorial over 10 factorial. Or 15 times 14 times 13 times 12 times 11. Right? 5 spots. You got 15 options for the first spot. Once you fill that one, you have 14 for the second. Once you fill both of those, you've got 13 options for the third, and 12 and 11. So so you get 15 factorial over 10 factorial, which is 360,360. So see how much the order matters. When order doesn't matter, you only had 3,000 options. When order does matter, you have 360,000 options. If there are 8 girls and 7 boys on the ballot, how many committees of 2 boys and 3 girls can be formed? So, going back to being combination, because the order doesn't matter. We're assuming this is the not, having a different responsibility here. But we're going to need to pick 2 boys out of 7 and 3 girls out of 8. So, combination of 7, choose 2, times the combination of 8, choose 3. All right, these are the boys, and these are the girls. So, we're just going to do the combination formula twice and multiply them together. So, 7 factorial over 7 minus 2 factorial times 2 factorial times 8 factorial over 8 minus 3 factorial times 3 factorial. So 7 factorial over 5 factorial 2 factorial times 8 factorial over 5 factorial 3 factorial. And remember that we can cancel some stuff, right? We can cancel from the 5 on down, so this is 7 times 6 over 2, 2 times 1, and this is 8 times 7 times 6 over 3 times 2 times 1. The 3 factorial is a 6, so that cancels. And so I would get 7 times 6 times 8 times 7 over 2. Or you could simplify something here. So 7 times 3 times 8 times 7. 1,176. And that's it for 3.1. Tune in next time for 3.2.